It's been recording this whole time.
Brilliant. Cool, so we're going to have a talk about binding energy per nucleon and why do we care about it in terms of nuclear stability. And so there's a really familiar, what will soon become a really familiar graph that you can expect to see in your exam. They'll often give you this graph in your exam and ask you to make interpretations from it. And all it is a graph of the binding energy per nucleon of every different element, every different isotope, plotted as a function of their nucleon number. And so the binding energy per nucleon tells us how stable the nucleus is. Remembering that binding energy per nucleon is the amount of energy that we need to completely separate a nucleus out into its constituent parts. And so the more energy that we need to do that, the more stable the nucleus is. And so what we can see is that we have a kind of peak of stability in the middle, and then as we move away from that peak to larger nuclei and smaller nuclei, they're less stable. And this also gives us like a pathway to understanding how we can get energy out of nuclear reactions. If we think about a fission reaction, that's taking really large, unstable nuclei, like uranium-235, that are over here, kind of around about the 7 point something mega electron volts per nucleon, and shunting them up this way into fragments that are closer to 8 mega electron volts per nucleon. Often, when we have fission taking place, it splits into xenon, that's about 140, and strontium, that's about 90. And so that split moves us from a uranium nucleus that has a really large number of neutrons that have been jammed in there just to make it as stable as possible, and it splits it into two smaller nuclei which are much more stable. And because we've moved from a lower binding energy per nucleon to a higher binding energy per nucleon, that difference in energy has to be emitted over the reaction. So that's how we get energy out of a fission reaction. So fission is moving that way, and we end up at something like 141 xenon and strontium 90-ish. When we have fission, it tends to split into two slightly uneven daughter nuclei, plus a few more spare neutrons. We'll talk about that later. Fusion, on the other hand, is when we take really small nuclei and smash them together. So normally when we're talking about fusion and like trying to make fusion happen to generate energy, or a fusion bomb, we're talking about taking isotopes of hydrogen, heavy hydrogen, like 2,1 hydrogen, and turning them into helium. And so fusion is happening at that end of the diagram, and we can see that the amount of energy we get from a fusion reaction is just humongous compared with the amount of energy that we can stand to gain from a fission reaction, because we're going from, if we start with heavy hydrogen, we're going from binding energy per nucleon of around about 1 up to helium binding energy per nucleon around about 7. So a massive change in binding energy per nucleon. Therefore, we're going to get a lot of energy emitted in a fusion reaction. We don't go straight from here to here. There's a kind of cycle of reactions that we can talk about later that happen, but that's where fusion's happening, that's where fission's happening. And so the similarity between them is that we're always moving from a low binding energy per nucleon to a high binding energy per nucleon to release energy because we've got a more stable nucleus. The weird thing is that we are taking over here a big nucleus and splitting it into two smaller, more stable fragments, whereas over here we're taking two small stable nuclei and banging them together to make a slightly bigger but much more stable nucleus. Both of those processes release energy because we're always moving to a higher binding energy per nucleon. Cool.
Fusion reactors coming soon.
Nuclear reactors coming soon. That's it.